section 3.1, linear approximation. Last time we took a look at this. The basic overall idea, to help you remember where we were, is that we had the idea of taking a graph of something that was not linear. Okay, it's got some sort of a curvature to it. And the image, sort of the big picture, was that we zoomed in on our graph and we said, if we zoomed in far enough, it's going to look like a line. What in the world is that line? Well, that line is actually the tangent line at that point. So if we take the tangent line at that point and we look at a point very close to it on the curve, then that point is going to be very close to it on the line. That's basically what we're doing. And so what we were doing with our graphs is that we were taking something that was difficult to calculate. So let me look at this one with you. So it's not simple to calculate the square root of 4.1 by hand. That's not something that you've ever really dealt with, right? But we can calculate the square root of 4 without a problem. You know what it is. It's easy, simple. So we can actually use that kind of information to create a tangent line at the x value of 4, which then gives me a line. It's got multiplication and division and subtraction and addition. Those are the basic 4 function things in your calculator, the basic 4 function things that you can do without a calculator. And we can calculate that tangent line, which we did. We got y equals 1/4 times x minus 4 plus 2. And we actually left it in that form. And the reason we did was because what we're interested in actually finding is what happens at the value 4.1. So we took the value then 4.1 and we plugged it in. We made a calculation. And we found out that the approximate value for the square root of 4.1 using this approach would be 2.025. And we compared that to the actual value our calculator gave us, which it uses a numerical approach as well. It doesn't actually really take a square root. It does something with reiterations and calculations, and it gives us 2.0248. So we talked about the fact that it didn't even differ until the thousandths place. So this is what we were doing last time. So everybody sort of remember the details. The idea is create a tangent line and then plug in a value at the end. We did the same example, or did the same thing with another example of sine of 1, and we talked about the fact that 1 is not a particularly friendly value inside of sine, but pi over 3, which is nearly 1, is quite friendly. It uses the unit circle. And so we did the same thing where we created an equation, y equals 1/2 times x minus pi thirds plus the square root of 3 over 2. And we plugged in our number 1, and we got an approximation of 0.842426, whereas the calculation in our calculator for just hitting in sine 1 would be 0.84147. So again, it doesn't differ until the third decimal place, the thousandths place. All right, so in general, we can extend this idea to a set of data where no formal equation for the function is given. Okay, so we don't have an equation for the next example that we're going to do. We're simply going to use the closest x values to the desired x value and the closest 2 points to calculate the slope nearby to our x value. So let me show you what that means. We're going to use linear approximation, linear interpolation, which is the same kind of an idea of linear approximation, to estimate the desired quantity. So we have a sensor, and it measures the position of a particle t microseconds after a collision is given. So we've got a set of data. Okay? Even the data doesn't really so much matter. The process is going to be the same no matter what the data was measuring. We're actually told that we want to estimate the position of the particle at time t equal 8, which you can tell is not in the table, and to estimate the position at time t equal 12, which again is not in the table. Okay, everybody good so far? So we're trying to figure out what is f of t when I do not have an equation. Now, I would expect, obviously, that if t equals 8, and my values around 8 are 5 and 10, that my function value is going to be between 8 and 14. Does that seem reasonable? Yep. I mean, that seems like a reasonable assumption for us. So we're expecting that the f of 8 value is going to be somewhere between 8 and 14, because f of 5 is 8 and f of 10 is 14. So that's something to be aware of first. If we get an answer that's sort of not between 8 and 14, we should be asking ourselves what went wrong. Why did that not work out? Because that seems a little weird. All right? Okay, so what we're going to do is we're going to take a look then that we have these particular values. Now, I chose these particular values that I boxed in here because those are the values that 8's sort of in between. They're the nearby values. Okay? So what we're wanting to actually make mention of is we want to create, basically, a line using this information. Well, if I have 2 points, can I create a line with 2 points of information? Well, absolutely. How do I do that? Yeah, so I need a slope, right? So how do I get the slope when I've got 2 lines?
Y's over x's.
Right, so this would be like 14 minus 8 over 10 minus 5, right? Okay, so what does that give me? 6 over 5, and we'll just leave it as 6 over 5, or you can put it in decimal form if you want to. That would be 1.2. And then we've got y minus y1. So we need to either use the 10 and the 14 or the 5 and the 8. Which one's closer to our t equal 8 value? Yeah, the 10 and the 14 are closer. The x value, rather the 10, is closer to 8 than 5 is. So that's the values we're going to use here for the y1 and the x1. So we're going to do y minus 14 equals the slope value, which we just found, 5 over x, times x minus 10 as the x value. You can simplify this all that you'd like. You can also, I'm just going to go ahead and move the 14 over and write it as plus 14. You can distribute out the 6/5 if you'd like, but we're actually really don't care about the equation. That's just sort of the intermediate step in this process. What we care about is the y value when the x value is what we're working with. In this case, it's 8. So what we want is we want to know what is our function value. I'll call it f of t since the notation here is not actually x's and y's. When my t value is actually 8 into my function. So you can do the simplification before and then plug in 8. You can do the simplification right now. It doesn't make any difference. What do you get? Sorry, this is supposed to say f of 8. What do you get when you plug in 8 into this equation of a line that we created? Anybody get a value yet? Except for you're working on it.
I'm getting 58 fifths. But
Can you tell me what it is as a decimal, Luke?
yeah.
Just because we want to make sure our value is really between 8 and 14. As a decimal form, I can 11.6. Does that sound good? Okay, 11.6. Is it between 8 and 14? Yeah. So this is a reasonable answer. This is the correct answer. So this is part A that we just did. All of that work was part A. And we're going to do the same thing with part B, but you have to recognize that for part B, I don't have the same equation of a line. Why not? Why am I not going to use this same equation? What's going to be sort of error or possible flaws if I did that?
Because the tangent line wanted the same information, maybe slope between those 2 points.
Yeah, I need different points, right? Okay, so that's the kicker. The first set of data gave me a t equal 8 value, which was between 5 and 10, but now I'm using t equal to 12, which is this information, and it may or may not actually match the same slope that I got before. Agreed? All right, so I need to calculate another slope. So my slope value is going to be between 10 and 15. So this is a y value of 18 minus 14 over 15 minus 10. What do I get for my slope for this one? 4 over 5. So I do, in fact, get a different slope, don't I? So I will, in fact, get a different line on this one. T equals 12. So what x value, y value am I going to use? Which one's closer to 12? Yeah, I'm still going to use the same x1 and y1 as I did on the first equation, but I have a different slope. So my y value, y minus still 14, equals my slope value, which I found was 4/5, times x minus 10. And I'm going to write it and go ahead and move the 14 over. Okay, so this is the equation I'm working with, and the x value or t value when I find this is actually what? T equals what? What am I working with here? 12. So I'm finding f of 12, and f of 12 is going to be, well, I'll just let you calculate it. I don't need to write it out. What do you get when you take 4/5 times 12 minus 10 plus 14?
78 fifths.
Okay, can we write it as a decimal so we can check the
It's 15 points.
15.6? In general, I don't care how you write your answer, is it decimal form or a fraction form. I just want us to be able to verify looking back, does this answer make sense?
Yeah,
Why?
because it's between 14 and 18.
Because it's between 14 and 18. The process that we're actually doing is called an interpolation. It means finding an answer in between two other values. That's what we're able to do. If we were estimating, like let's say I was asked this same question with this same data set, but it wanted to know the t-value at t equal to 16. Well, I could still use this process, and I'd still have to use the 10, 15, 14, 18. I'd still have to use that same boxed in part that's in purple. It's just, it wouldn't be called interpolation anymore. It'd be called extrapolation. So extrapolation is sort of making a claim outside of the designated area that I know for sure information about. Interpolation is making the claim for inside that data set of information. Okay? So we could still do it. It would just not be called interpolation.